Hello, my name is Chance Hattrick, and this is my grade 12 long ISP, the Enigma machine, part 1. The point of this project was to create a device that can encrypt any one of these 30 characters from A to Z, as well as 4 types of punctuation: space, comma, period, and colon. And in addition to that, not only will it encrypt a message, but depending on what rotor positions you use, it can also decrypt that message entirely. So, for example, with the current rotor positions I have on this machine, when I press the letter A, you can see it encrypts into the letter L. Now, currently, if I were to press L, it would encrypt into the letter C. Now, if I were to restart this program again, I would have the starting rotor positions I had when I pressed A. And when I have that, when I press L, you can see that it encrypts into the letter A. And this allows us to encrypt and decrypt any message that is taken using this machine, so long as we have the rotor positions. This project can be separated into 3 key parts: the keyboard matrix, the Charlie Plex PCB, and the internal rotors. In this video, I will be going over all 3 and explaining also what I plan to do in part 2 of this project. The first part, and arguably the most important aspect of this part of the project, is the keyboard matrix. You may be wondering, what is the difference between a keyboard matrix and just using PBNOs? Well, when we look at the schematic for a keyboard matrix, you will see that we have individual PBNOs connected to the same 2 pins. For example, PBNO 1 is connected to the same row pin as PBNO 4. So why is that? Why don't we just connect each one of these to their own individual pin? Well, this is because with 30 PBNOs, you will need to have a large number of pins to accommodate a large number of characters. And because we're using an Arduino Nano, we need to significantly reduce the number of pins used. So in this example here, I am controlling 9 PBNOs with only 6 pins. But how am I doing it? Well, what the keyboard matrix does is it scans each of the columns individually. And all of these rows have an input pull-up pin on the Arduino, meaning they usually read high. So that means if we have all of these columns here, and we individually set one column to low, if a button is pressed, this input will read as low. If not, it will read as high. And because we're scanning these columns one by one, it doesn't matter if we press this pin, this PBNO, and this PBNO, the program will not get confused. And it's with this schematic here that we expand into a 5x6 keyboard matrix that allows us to control 30 PBNOs at once. The other PCB I will be going over in this project is the Charlie Plex PCB. Now, the Charlie Plex PCB has been covered in one of my previous videos about the Charlie Plex clock. So here I'll be giving a very brief summary. This 30 LED Charlie Plex PCB can be broken down into this 6 LED Charlie Plex schematic. In this scenario, we're using 3 pins to control 6 LEDs. And how are we doing that? Well, if we were to set P1 to high, P2 to low, and P3 to input, only these 2 pins would be able to complete a circuit. And the only LED that would allow it is LED B. And so LED B would be the only one to turn on. Alternatively, if we were to set P2 to high, P1 to low, and P3 to input, LED A would turn on. And additionally, if we were to set this to P1 to high, P3 to low, P2 to input, then LED E would turn on, and so on. And so using this logic, we can expand this into a 30 LED PCB, which would require 6 pins. And this allows us to not only control 6 30 LEDs effectively, but it also reduces the number of pins we need and allows us to use a Arduino Nano rather than a much larger MCU such as the Arduino Mega. The code that controls the Enigma machine, everything from the LEDs to the keyboard to the rotors. In this section of the video, I'll be covering the rotors and the reflector. So, how the rotors and reflector work is that when you take a rotor, you click a button, say A, which would take you to 4, and then this 4 would take you to the 4th position of rotor 2, which would take you to the 18th position of rotor 3, which would then take you to, say, the 20th position in the reflector. And now at that position, you may wonder, how is the reflector different from the rotor? Well, for the reflector, rather than randomly arranging the values, they're instead swapped. So the 7 is in the 3rd position of the reflector, and the 3 is in the 7th position of the reflector. After going to the reflector, we go back to rotor 3, and then 2, and then 1, essentially doing the inverse of what we previously did. What this does is it creates a pathway between two characters, say A and L. So when you encrypt a value, say you encrypt an A into an L, when you want to decrypt it, all you need to do is set up the rotors in the same way as when the A was encrypted, and then you'll get your value. Now, every time a button is pressed, the rotor 1 is shifted 1 to the right. Every time the rotor 1 has shifted right 30 times, rotor 2 will shift right once. And every time rotor 2 has shifted right 30 times, rotor 3 will shift right once. What this does is it creates thousands of unique rotor combinations that the user can use to encrypt and decrypt their message in unique ways. And because these rotors are entirely customizable, you can completely change the configuration of these rotors and the reflector to design to your preference. Now, these are done through functions. So, for example, we have a function for inverse rotor pass as well as rotor pass. And so one goes from rotor 1 to 3, and the other one goes from rotor 3 to 1. We also have a reflection pass, and this is all done in the encryption function, which is then used in the read matrix function, which takes our input letter and encrypts it and then outputs it on the get LED function. And finally, we have the change rotor function, which allows us to increment each of the rotors 1 to the right based on a button press.